All right, in this section, we're going to finish out this chapter learning how to solve equations that have fractions. So our first step when we're working with an equation that has fractions is to just turn it into an equation with no fractions. Once we're done that, we should be looking at an equation that we already know how to solve. So the technique that we use to turn it into an equation with no fractions is to multiply each term in the equation by the LCD, by the least common denominator of all the fractions in the original equation. So we're going to start here. Here's a simpler one. The denominators are just numerical. So the LCD, the least common denominator, that's the least common multiple of 12, 8, and 6. And in this case, that'll be 24. So what we're going to do, essentially what we do here is we say, I'm going to multiply both sides of the equation by 24, right? We know that we're allowed to multiply both sides of an equation by the same thing. And then on both sides, if there's distributing to do, we distribute it to each of the terms. And that's why here this says we just multiply each term. So I always start out by writing out the equation again, giving myself space. Because I'm going to zap each one of these terms with the factor 24, which I'm writing as 24 over 1, just to kind of help make the reducing simpler. Now, the reason we're multiplying by 24, the reason we're picking 24 is because I know all of those denominators will cancel, right? 24 is the common multiple of all of those denominators. So I'm going to do that first. So I'm going to cancel. 12 goes into 24 twice. 8 goes into 24 3 times. 6 goes into 24 4 times. So our first term is 2 times x, or 2x. All of these denominators are 1, so I don't need to write them as fractions anymore. Minus, let's see, that second term is 3, equals, and then on the other side we've got 4 times x plus 2. This is a linear equation, and we know how to solve linear equations. So I'm going to just sort of go over here so I have a little bit more room. So I got 2x minus 3 equals, we're going to distribute that 4x plus 8. And then, get all of our x's on one side. Get the constants on the other side. So again, negative 2x is equal to 11, and now we just divide both sides by negative 2. And we get negative 11 halves for our result here. Let's do another one here. In example 627, our equation is 5 over n plus 2 is equal to 3 over 2n. So, you always want to start by factoring denominators, and in this case, they're already factored, right? n plus 2 cannot be factored. 2n is already factored. It's 2 times n. And we want to identify our LCD, and 2n and n plus 2 have no factors in common, which means I need to pick up all of those factors, 2, n plus 2. So now I'm going to multiply both sides by the LCD. So let's see. The 2n's cancel on the right side. On the left side, the n plus 2 cancels. And this fraction becomes 2n times 5, or 10n on the left. On the right side, 3 times n plus 2. There's a nice linear equation, another linear equation to solve. We know how to do that. Let's distribute the 3. We can subtract 3n from both sides. So now we've got 7n equals 6, and now it's all over but the shouting. And n is equal to 6/7. When you're solving an equation with fractions, one thing you want to just make sure you check at the end, if your fractions, if any of your fractions have a variable that lives in the denominator, you just want to make sure that what the value you found is an allowable value for the denominator, meaning just check to see if it leads you to divide by 0 if plugged into the original equation. We can see that we're all set here. N can equal 6/7. The only values that make us divide by 0 would be -2 would make that denominator 0, and 0 would make that denominator 0. So there's no issues here, but you do have to make sure if you solve an equation and you get a result that leads you to divide by 0 in the original equation, that means that value you found is not actually a solution to the equation. Let's do another one. Here we're going to solve this one for x, and I'm going to start by rewriting this equation. I'm going to start by factoring denominators. The only factoring that we need to do is in that first denominator, because we could take out a 2. And then I give space because I know I'm going to need to multiply through by the LCD. Before we do that, we have to identify the LCD. Maybe you want to take a look, maybe you want to pause the video and see if you can take a stab at the LCD before I tell you what I get. Looking at the factors that we have, our LCD will be 4 times 2x minus 3. I need the 4 because I got to make sure that middle denominator is taken care of. Once I grab the 4, that this factor of 2 is already covered, right? The factor of 4 contains a factor of 2. And then, of course, I need the 2x minus 3. Now we're going to proceed by multiplying through by the LCD. Oh, whoops. I wrote 2 in these ones. That should be a 4. The reason we're multiplying by the LCD is because we know that will make everything cancel in the denominator. So let's go through and cancel what will cancel. This 2 cancels with one of the 2's. 2 goes into 4 twice. The 2x minus 3 cancels. So this first term is 2 times 3, or 6. In the next fraction, the 4's cancel, and we have 2x minus 3. And then on the other side of the equation, the 2x minus 3's cancel. We're left with 5 times 4, or 20. I'm going to combine some like terms on the left side. So 6 minus 3 is a plus 3, so the left side becomes 2x plus 3 equals 20. We can subtract 3 from both sides. And now divide by 2. So x is 17 halves. And, you know, again, as I mentioned at the end of the last example, we want to make sure that this doesn't lead to division by 0. But the only things that will lead to division by 0 are whatever leads this LCD to be 0, and so that would happen only if this factor is 0, and 2x minus 3 is 0 when x is 3 halves, which is not 17 halves, so we're all set. This value does in fact solve, and you can check, you know, like any equation you solve, you could check if you plug in 17 halves in for x into the original equation. It'll work. So let's try this one. There's a little note that says extraneous solutions at the beginning. We're going to solve this, go work through this problem, and then we'll talk about what extraneous solutions means. We need to start by factoring. Now, the first two denominators are already factored, but that last one, x squared plus x, will factor. So I'm going to rewrite this. I'm going to make sure rewriting it to give myself some space. And then I'm going to put this minus up top. And then in the bottom I've got x times x plus 1. So the LCD for this equation is x times x plus 1. And if we multiply all terms by x times x plus 1, and then let's see what'll cancel. All of our denominators should cancel, right? So the x plus 1 cancels with the x plus 1. So that first term is 2x. And those x's cancel. So we're subtracting x plus 1. Note the parentheses here. Those are really important. I am subtracting that whole remaining term. So I have to use parentheses. And then over here, on the other side, the x cancels, the x plus 1's cancel, and we're just left with negative 2. So now we could solve this. I'm going to distribute that negative over here. So 2x minus x, whoops, minus 1 is equal to negative 2. I'm going to add 1 to both sides. And then 2x minus x, that's just x, equals negative 1. All right, so now take a look at the solution and compare it to what we have in our denominators in the original equation or in the LCD. You'll note that if x is equal to negative 1, it actually makes this denominator 0. It also makes that denominator 0, right? So this value of x that we found does not solve the equation. This is not an allowable value for x in our equation because it makes us divide by 0. So first we're just going to observe that this leads to division by 0. In the original equation. Now, we didn't make any mistakes when we solved this, right? X equals negative 1 is a solution to like that equation, right? The equation we got once we cleared denominators. However, it's just not allowable for x to take on that value in the original equation. So since the only value we found going through this process cannot be plugged into the original equation, that means that there is no solution. There's no solution to this equation. All right, we're going to finish this section by doing a couple of word problems. So I know that's everybody's favorite thing. But the word problems in this section all kind of read similarly. Usually we're talking about some sort of task that needs to be completed, whether that is, in this case, emptying a pump emptying a tank, or it might be a vehicle traversing a distance, right? There's some task that's being completed. Now, usually then also in these we are comparing two either crews that are performing the task, or in this case, two different pumps that might be performing this task of emptying the tank. And they work at different speeds. They work at different rates. So this tells us in example 630 that one pump can empty a tank in 7 hours. Another pump could empty that same tank in 5 hours. If those pumps could work together, how long would it take to empty the tank? So, you know, just starting out, we'll note that the amount of time it should take these two pumps working together should definitely be less than 5 hours, right? Should definitely be less than that faster pump working by itself if it's helped out by another pump. So I like to kind of just start out these problems kind of getting a sense in my mind of like what I think, you know, what a reasonable range of values might be for this result. But I'm gonna just sort of one of the underlying kind of relationships for helping us make these equations. You know, we're already familiar with the equation that distance is equal to rate times time, right? But we can generalize that, and for us, it's really any old task is completed by having some crew or some pump or whatever working at a particular rate, however fast it works, times however long it's working. Right, so now this one pump, they gave us the rate. They didn't give us the rate in like liters per minute or gallons per hour or something, but they did tell us how long it would take to complete, to pump one full tank, to empty a tank. So pump number 1. Says one pump can empty a tank in 7 hours. So its rate is this one tank per hour. Per 7 hours. That's its rate. Pump number 2, that's the faster pump, can empty the same tank. Now it's only because we're talking about the same tank that these rates are comparable to each other. Can empty that one tank in 5 hours. And what we're going to do is have them work together to empty this tank. So the way that we're going to make this equation is going to take on this form is the work done by pump 1, like the amount of tank that pump 1 empties, plus the amount of the tank, the work done, or the amount of the tank emptied by pump 2, and all that is going to equal this one task, or emptying one tank. All right, so each of these here is a rate times a time. So pump number 1, its rate is one tank per 7 hours, so 1/7, times the time. Now the time is the thing we don't know, right? It says, how long will it take for the two pumps working together? So that thing that we're trying to solve for, that's our variable. We'll let t be the time spent working together. So pump number 1 is working at the rate of 1/7 for t hours. Plus pump number 2, its rate, one tank per 5 hours, so it's a rate of 1/5 times t hours, and that's equal to one tank. There's our equation now that models this problem. It's an equation with fractions. The LCD is 35 in this case. So I'm going to multiply everything by 35. 7 goes into 35 5 times, 5 goes into 35 7 times. So we have 5t plus 7t is equal to 35. And that's a linear equation, pretty simple to solve. 5 plus 7 is 12. 12t is equal to 35. We'll divide both sides by 12. Now, a lot of the time I would just leave an answer as a fraction, but there's some context here. We're trying to figure out how long it takes. So I'm going to do the division on the calculator and see what we get. 35 divided by 12 is 2.92 hours. Note that that is in keeping with about what we thought. We knew it would be less than 5. Also, it makes sense that it's more than 2.5. It would take 2.5 hours if both the pumps we had could empty the tank in 5 hours, right? Then you just double they're twice as fast. But it's actually being helped out by this slower 7-hour pump. So it makes sense that that time is more than 2.5, and we knew it had to be less than 5. Okay, let's try another one. This one's similar. We got 2 crews working on painting a structure. One crew could do the structure in 15 hours. If a second crew joins them, they can paint the structure in only 8.5 hours. That's together, right? If a second crew joins them. So that's the time it takes together. How long would it take the second crew to do the job if working alone? Well, let's sort of try to set it up like we did the last one. So we have crew number 1 and crew number 2. Crew number 1, they give us a rate. It says it can paint the structure in 5 hours. So that's like 1 structure per 15 hours. That's its rate, 1 over 15. Crew number 2, we don't know how long it takes. That's what we're trying to find, is how long it takes to paint that structure working alone. So there's where our unknown lives. So it's 1 over t is equal to the rate. And we know that the time working together is 8.5 hours. So let's put this together, just like we did with the pumps emptying the tank. So we have the work done by crew number 1 plus the work done by crew number 2 and together they are performing one task. Right, or painting one structure. So each of these is a rate times a time. So crew number 1 is 1/15. That's its rate times the time. They're working together. We know the time working together. That's 8.5. The work done by crew number 2, that's a rate times the time. Its rate is 1 over t times 8.5 hours. And together they're performing one task. So here's an equation that models the problem. We're going to clear denominators. Let's multiply through by 15t. So in the first fraction, the 15s cancel, and we're left with 8.5t. In the second fraction, the t's cancel. 15 times 8.5 is 127.5. And this is equal to 15t. Again, a nice linear equation. So to solve this, I'm just going to subtract 8.5t from both sides. And 15 minus 8.5 is 6.5t. So, and now we just need to divide. $127.5 divided by 6.5. That is 19.6 hours. And that's how long it would take crew number 2 working alone.